So with that, I'm going to hand it over to Dave and let you take it away.
So I guess we talked about, Thomas and I talked about this when I was here for one of the cloud talks a few months ago. And we got talking about the singularity. Somehow that topic keeps coming up whenever I'm in a conversation. And the background of this for me is that I work with a professor over at the university on a company that is now a side project, but it is actually a going concern called eCortex. And that company is based on the research of Professor O'Reilly at the University of Colorado, and his work is making brain models in simulation. In other words, he builds simulations of neurons working together to perform cognitive functions. And this is a scientific area that goes pretty far back, back to the 80s, I would say, early 80s. But it has advanced tremendously in the past couple of decades. And that's how I first got involved in this. And then one of the big topics of conversation in Randy's lab is the singularity, because in fact, that is sort of what they're working toward in a sense. And so we will get into kind of what that means. All right, we have slides. So this is an introductory talk. I'm going to talk a little bit about what the singularity is and what it means and why it's called that. I'm going to talk a little bit about some of the progress that's going on in science and research today that suggests that this proposition of the singularity is not necessarily far-fetched. It's not necessarily ridiculous, and in fact, it's probably going to happen. And then we'll talk a little bit about scenarios for the future, what that might entail, what it might mean. In the introductory paragraph, if you happen to see it on the website, on the DaVinci website announcing this event, one of the suggestions I make is that it kind of supersedes or masks all other attempts at futurism. In other words, looking at the future becomes very difficult because of the singularity. So let's get into it. Try not to move too fast. So again, the three areas that we'll go over is what is the singularity, what are some examples of recent progress, and what are some scenarios for the future. So how many people here know basic college algebra, comfortable with it? About 10%, okay, 15%. All right, so the reference to a singularity is a mathematical concept, and a singularity is a place where a function is not defined at all. If you think about just dividing by a number, if the number happens to be 0, then there is no value for it. So that's a mathematical singularity. And just to show that 1 over x is not the only example of that, tangent function looks like that. The concept of a singularity comes up in physics. It doesn't really make sense in physics, and yet mathematically it comes up in quantum mechanics, it comes up in relativity. So this idea is talked about in many different contexts, but the general idea is that you don't know what it is. In a couple of the slides later, we'll see exponential functions. You'll also see one. It's supposed to be an exponential on my shirt, but it isn't really. An exponential function is one that grows extremely rapidly. Population growth, for example, is an exponential function. And this is an exponential function here, and one of the interesting things about it is that it does not actually have a singularity. So the point I'm trying to make here is that the concept of the singularity is a metaphor for a time when we don't really know what's going to happen. We don't know what it is. It's, at the present time, it's undefined. Okay? Who knows who John von Neumann is, or was? Not too many people at all. Okay? He was a polymath who, he was a mathematician, a physicist, a computer scientist, contributed in many fields. But the important thing to know about him in this context is that he is the creator of what is called the von Neumann architecture for computers, which is the architecture that basically every computer that anybody ever has had uses. All of your Intel PCs, all of your Macs, all of your iPods, your iPhones, even your watch probably has a von Neumann architecture in it. And so the reason I bring that up is that he's a pretty smart guy, has contributed in important ways to both practical and applications of computer science. And he was probably the first to use this terminology of the singularity. And this is the concept, is that there will come a point where things are changing so fast. You may have noticed that things keep changing faster. There will become a point where things change so fast that we won't even be able to recognize them and keep up with them. That we can't really even look a little bit ahead and tell what's going to happen. Did I skip a slide? No. Who's familiar with Moore's law? Okay, more people. Moore's law says that every 2 years, the number of transistors on a chip will double. It has been true since 1970. This only goes up to, it looks like, 06. It continues to be true. The first time that somebody said that physics was going to prevent it from happening, I remember going to a lecture in 1982 at MIT where they said in 2 years, Moore's law will stop. They were wrong. And it continues to go. So there's actually an extant picture of an iMac from 2001 and an iPod from 2009 or something. Some of you may have seen that picture. And they have, the iPod has more computing power than the iMac. And this is the level of progress that we've seen. This does not look like the exponential curve I showed you a minute ago. But the reason is that the vertical axis is compressed on a logarithmic scale. So this is, in fact, a very, very, very steep exponential curve. Who's heard of Ray Kurzweil? Okay, that's good that I'm giving an introductory talk if you haven't heard of Ray Kurzweil, because he is the promoter behind the singularity. He's the salesman. He's a technical guy, but he is out there talking about it every day. That's kind of what he does now. And he came up with an interesting idea in one of his books. And if you're interested in this stuff, definitely read his books. He's kind of a psycho, but he's right about a lot of things, and he's very, very clever and has thought a lot of good ideas, so worth reading and thinking about. His extension says that Moore's law is just a very special case of a much more general principle. And the first generalization he provides is this idea that the power of computing has been exponentially growing way back. Actually, in one of his books, he actually goes back to like the abacus and tries to extrapolate it. But the idea here is going back all the way to 1900 when we first had electromechanical calculators. Computing has grown exponentially. And so the idea is that this is not just a case of one particular technology with microcircuits, but is in fact a general technology concept. And in fact, he came up with what he calls the law of accelerating returns, that technology will increase exponentially because the technology we have today is being used to create the technology of tomorrow. And that technology of tomorrow is used to create further technologies. And so that's one of the places where exponentially increasing technology comes from. So the idea is that this is a very general principle, and whether or not that proposition is true, it seems to be the case, at least in computing today. It does not seem to be the case in some other areas, right, like energy production, et cetera. But let's get to the main topic at hand. What if we could apply that law of accelerating returns to intelligence, to treat intelligence as a technology where we could make it better at an exponentially increasing rate? And the way I think we need to do that, and the way Kurzweil talks about it and others talk about it, is via this idea of reverse engineering the brain. Does everybody know what reverse engineering is? The idea, okay, the idea is to figure out how something works and then reproduce its function. Usually it's illegal, so it's one of these things that you typically sign a software license, for example. It says that you cannot reverse engineer the software. In this case, since it's up here, we're allowed to. And the idea is that we're trying to figure out how the brain works, in part by simulating, and in part by getting other data sources. This is a picture from, I mentioned at the beginning, eCortex and Dr. O'Reilly's lab. And this is a picture that is not very clear at this point of a model of the visual system in the brain. And you can see the picture that the model is looking at is a cat, or maybe it's a lynx or something. And at the very bottom, you can see that some of the shapes in the image are actually reflected, and that does actually, we know that that happens in the brain. And many of the effects that are happening here, each dot represents an individual neuron in your brain. So the idea here is that this is the kind of, and in Kurzweil's books, you'll see similar pictures, although they're not from Randy's models, right? So the idea is that we're trying to figure this out at a neural level. We're trying to figure out how the brain works, how it's architected, and why it does what it does. Now, I think I'm not going to get into that right now. Let's suppose that we have some success at this, that we're able to actually produce intelligence. This is a relatively long passage, and I'm going to, there's a ... at the end, and I'm going to finish that passage with one sentence. I took one piece out here. But the idea is that if we created something that was intelligent, that genuinely intelligent in a simulation, in a computer, and it was as smart as we were, then it would be able to create the next set of inventions. We wouldn't need to. And in fact, there are all kinds of interesting and deep philosophical questions about what is the status of that entity, right? Is it a rational being? Does it have the same rights as we do? Is it all these things that come up in, whoever was saying they saw the movie AI last night. I mean, all these issues come up pretty quickly. In fact, in the lab, we argue about them and frequently disagree about, should we even be doing some of these simulations? Are we killing something, right? So, but the point from a singularity perspective is that as we reach the point where these entities are intelligent and they surpass us, we won't need to invent anything else. That will be the last invention humans need to make. So another term for the singularity is the rapture for nerds. And some of the things that are expected to come out of it are, well, they'll cure disease, and we'll live indefinitely, and we'll be able to augment humans if we want to. There's an idea that these beings will be our evolutionary successors, so we're just the last wetware intelligence, and then now we go on to electronic intelligences, or however they, I'm sure they will quickly invent something that's non-electronic and uses some other technology. All of the current problems that we worry about, energy and food production and drugs and those will all go away because the robots will solve the problem for us, and it's going to be awesome, maybe. So let's talk a little bit about some of the recent progress in this. How am I doing on time? Oh, just about right. So this is a program at DARPA that is ongoing now. I think they've funded about $30 or $40 million total. No, that's just IBM's share. So this is a substantial program at DARPA, maybe a $100 million program so far. And you notice that those graphs and some of the little points that they make, it's a little hard to read, are very singularity-esque. You see on the right there, it says, human-level performance, dawn of a new age. And you are paying for this. This is at DARPA. But there's this idea that, and there's von Neumann's name again, where we start to run into problems. The complexity of the machine exceeds the complexity of the environment, and it doesn't really work anymore. And so another idea that the von Neumann machine, really does have limitations, and so we want to take a different approach. And the idea here is that we will use something that looks more like the brain. Okay. And in fact, they are starting to do this with a technology called memristors, which are memory transistors, if you will. So the idea is that you have inputs on the left, the pre-neurons, where it says pre-neurons, those are the inputs. And then at each point, you have a learning synapse, which is an equivalent to a neuron in the brain, neuron synapse in the brain, where the neurons connect to each other and talk to each other. And then that output goes to the outbound neurons. And so they're actually building a chip, but the key idea is that the transmission is dependent on the history of transmissions before. It learns just like the brain does. Okay, so there's this idea that conceptually it's very similar in principle to what the neurons in the brain are doing. So they've built a small version of this thing. I think it only has 256 neurons so far, and their goals are, you know, some massive number of neurons eventually over the next few years. But they have actually built one that works. And this complicated thing, the small print that you can't quite read says temporal lobe, occipital lobe, and basal ganglia, and I can't quite read all of them. Frontal lobe, which may be terms familiar to you if you know anything about the brain. Those are pieces of the brain. So they're trying to actually simulate components in the brain with this chip. Again, it's trivial in size, so it doesn't really do much yet. But the idea is that they're actually building circuits that will emulate the brain fairly directly, unlike the simulations I've talked about before, which are done entirely in software and can't possibly cope with the volumes of neurons that we have in our brain, which is 100 billion, is that the latest? Something like that. I'm looking at Seth. So I'm going to talk about another, did I skip a slide? No. Talk about another area. This is a project that eCortex worked on, and I'm going to use it as an example because it represents very incremental progress. It's not a massive advance. It just kind of illustrates the idea that this is very nitty-gritty engineering that people are doing. It's not kind of sitting in a professor's room and fantasizing about how we might create artificial intelligence, which is the way that artificial intelligence started. And I often refer to it as 50 years of failure, because the artificial intelligence community started in about 1960 or so, and basically created a lot of theories about how things might work, and nothing ever really worked at a level of actual intelligence. So figure ground segmentation is the idea that in an image, when we look at something, we have to separate the thing that we're interested in from its background. Here, we're clearly interested in the cougar that's about to eat us, and we're not as interested in the tree. But if you actually tried to process that using software, it's a very, very hard problem. Knowing where the cougar is and the tree isn't is an extremely difficult mathematical and computational problem. And the idea of recognizing an object just in a plain background, where there's no complex background, that's largely solved. And I'm not going to explain exactly how it works, but the idea is that early on we process simple features in our brain, and we kind of merge the different areas that we're looking at, or different areas of our visual field together, and then so it doesn't matter where in the visual field we see it, we still recognize it. It's a very interesting process, and it's very well understood, not only in simulation, where we can actually reproduce most of the functions, but also they've done unit cell recordings inside brains to know what the individual cells are doing. So this is a very well understood problem. Partly because animals have visual systems. Language is not very well understood, and you can imagine why that is. Animals don't have language. So this is a set of objects that a model of eCortex has, that it recognizes, not just recognizes these pictures, but it recognizes brand new exemplars of those same object categories. So they're kind of small, you can't really see them, but this is a floating balloon, and a frying pan, and a computer screen, and a tape dispenser. And if you give it a new exemplar and a different orientation, it can still recognize that object. Turns out that's also a very hard problem, and the reason it's successful is it does it basically the same way that the brain does. But when you try to isolate the background from the foreground, all of a sudden it blows up. The nature of the problem is that it starts to link up all the leaves in the tree with the spots on the cougar, and it gets confused. So what we tried to do in this particular project was a new approach to isolating the foreground from the background. And I don't know if you can see the cyan line on the top is where we don't process any figure ground. We just look at it raw, and that had about a 30% success rate, 60% success rate, excuse me, and maybe 5% of difference. Okay, so it was better. We made some progress, but it's engineering, and this is very nitty-gritty, day-to-day, making it better, tweaking it, trying to understand better what the brain does, going back to the model, fixing that. It's very hardcore. Let's get into some of the biological stuff. I'm going to talk about several different kinds of prostheses that we have, and this gets into more cyborg sort of singularity stuff, where the idea is that we don't just create simulations, we reverse engineer the brain by actually merging things together, right? Merging mechanical and electronic things with our brains I'm not sure what the metaphysical status of that would be, but it actually does make progress toward the goal, because now we're creating something that's probably going to be superior to us if we can connect it all together. The retina is actually part of the brain. You realize there are neurons that are in there, and so this is an example of a retinal prosthesis where they have a video camera, connects into the retina, stimulates it. So these are actually the electrodes in the middle picture, and on the right it shows how it's actually connected into the neurons in the retina. And the video stream actually inputs there. Formerly blind people can see. Now they can't see the way you and I can see, but they actually can navigate their way around a room. They perceive objects. They have a certain level of perception. So it's still very early stages, but these are actually starting to become used, and this is only one example of many labs that are doing this kind of thing. This is actually from a few years ago. And that's actually a picture of the electrodes right in the monkey brain. And what they did was they connected 200 electrodes to a monkey's brain, followed the patterns, decoded them, and then were able to learn from that and reproduce the motion of the monkey's arm based on the patterns of neural activations gathered from those electrodes. Okay, so we're starting to understand, and that motion, I think they created another arm that moved like the monkey's arm did, and it followed the monkey's arm within about 5% of the motion, of the range of motion. So it was a fairly close simulation with only 200 electrodes, which is very interesting because there's probably tens of millions of neurons that that are used for the monkey's arm motions. And so the idea is we're starting to decode the neural signals. We're able to interface with motor devices. This could be a prosthetic for someone who's lost an arm, right? You could have a mechanical arm, all kinds of applications for this. This is very recent and really interesting. This is the only picture I could find, and it's really just some stuff from the paper, but the basic idea behind this experiment was that they taught a rat how to do some task. They then, with pharmaceuticals, stopped the rat's hippocampus, which is a memory center, from working. The rat no longer could do the task, not surprisingly. They then implanted a neural prosthesis that was trained based on what they had previously been reading with an implant in the rat's brain, and replaced the hippocampus with the implant. Now it could do the task again. So they could just switch it on and off as to whether it could do the task. So it actually had a neural implant that was replacing part of its brain in it, and it worked. I don't know about you guys, but my memory is not any better than it was a few years ago. So this is progress as far as I'm concerned. So this is an interesting one, and this is not something people normally think of as singularity progress, but Vernor Vinge is a science fiction author who, he's not the first to talk, he wrote the first paper kind of on the idea of the singularity specifically. And this is kind of funny, actually, almost, because he wrote this in 1993, and he says, "When I began writing, it seemed very easy to come up with ideas that took decades to percolate into the cultural consciousness. Now the lead time seems more like 18 months. Or maybe 30 seconds, right? There has definitely been an exponential decrease in the amount of time that it takes us to propagate ideas and memes and information and to gather that information. And this is really important because remember the concept that last year's technology is used to create next year's technology. The idea here, the reason that this contributes very strongly to exponential growth of technology is that the right scientist at the right time can get the right information, and that was not always true. You used to have to go to the library. The books in the library are 10 years old. The journals in the library are 6 or 8 months old, right? And by the way, even today in academia, if you write a paper, you do some research, and you write a paper, between the time that you made the discovery and the time that regular non-special readers of that journal see it, it's still about 18 months or maybe 2 years. Now, there are propagation mechanisms that are better now, but it's still actually slow in academia. And so these kinds of things really make it possible for ideas to go faster and faster, so that it's used for all kinds of different things, including revolutions, but it's also used in science, which is the thing of interest here. I thought I'd give some examples of things that are, in my view, not singularity progress. And there are really two different categories here. One is the Watson Jeopardy game. People mostly heard about that, where IBM had a computer that actually won at Jeopardy against a couple of human opponents. And most people remember Deep Blue, the chess computer that beat Garry Kasparov pretty convincingly. Those are not examples of singularity progress because they're what I call narrow AI. And I want to go back to what I said about the AI field as it first began, tried to start from inside out. It tried to figure out what the mind was doing and emulate that in a computer. That doesn't really work. We have to reverse engineer the brain. But some of the ideas behind it can be used for narrow applications. And lots of people have Roombas, and they go around the house and actually sweep up the floor. And we have lots of technologies that are very effective at solving very narrow problems. The thing is, that's not intelligence. That's just a machine that is well designed for its problem, and it happens to use information technology to solve that problem. That's great. It's all good stuff. It makes our lives easier, and maybe that's the way to avoid some of the not necessarily as good scenarios in the singularity, but it isn't intelligence. Similarly, the autonomous vehicles like the Google car, if you've heard that, they actually got approval to run those in Nevada. I think now they can use driverless cars in Nevada, and then the Predator drone, which is actually used very effectively in some of our conflicts in the Middle East. These can ride autonomously. They're not just always radio controlled, although most of them are used. There's still a human involved in the loop, but they can actually fly themselves home if they have to. So these are autonomous vehicles. They can drive themselves around. But again, that may seem like a pretty broad problem, but it's actually a pretty narrow one when you think about it. And the Google car can't just drive everywhere. It can't drive in Boston, I'm guessing. So let's talk about where this leads. The first question is not quite as scary a one, but and this is my attempt at alliteration, but cyborg or simulated sentience. So a question arises, what will come first? Will we simulate brains operating completely like the human brain and have something that's intelligent and artificial and that we've built, but now is its own intelligent thing? Or will it first be the case that some of these prosthetic ideas come to pass, and that we have kind of augmented humans that are superhuman that can do things that you and I can't do, at least today? There's no obviously clear answer to this question, right? It seems to me from the progress in the field that a lot of the augmentation things are going to be happening pretty fast. And the reason is that there are motivations for them that go beyond just wanting to create it. In creating simulated sentience, there's actually a negative motivation because a lot of the dollars go to narrow problems. If you look at the Department of Defense, which funds a lot of research, their problems that they want solved are particular. They're not general. And as one of the things we learned at eCortex and has been known for a long time is that neural networks, the old line is neural networks are the second best solution to everything. And every word there is important. So they're the second best solution, but to everything. Well, that's true of people too, if you think about it, right? I mean, we're being replaced by machines in various ways all the time, and it's been going on for centuries. And if you narrow the problem enough, you can build a machine that solves the problem better. So there's a strong drive toward, again, what I call narrow AI, which is problem solutions that are narrow. Whereas funding and research effort for more general intelligence and reverse engineering the brain ideas, that's harder to come by because it's not clear what exactly it's going to solve in the short run. Your time horizon, it's much longer. Clearly, DARPA has been thinking about this. And The good news is DARPA actually has taken a little longer range view than they were a few years ago, but still, it is certainly not well accepted, and most of the research dollars go toward narrow AI, which again may make our lives better, but isn't going to get there from an intelligence perspective. The cyborg thing has medical benefits, immediate medical benefits for people who need prostheses, who have memory problems, and then beyond medical things, there's the motivations of wanting to be superior. We all have that alpha instinct to want to take it one up. And I was at a conference. This was like 12 years ago, where there was an argument as to whether people would like put things in their brain to make them smarter. Like they put things in their nose, right? For no apparent reason at all. And so there's significantly decreasing shyness about augmenting yourself in one way or another. And the idea that you could get some kind of advantage, I don't know what this thing does, by the way. It's, this I don't even know where that comes from. This is from Bicentennial Man, by the way, if you haven't seen the movie. Actually kind of a fun movie. And I don't know where that comes from. It almost looks like this, it's not Star Trek, is it? In any case, the idea that we could connect directly to Google and just think things, and the results would kind of just appear in our thoughts, right? Wouldn't that be powerful? Wouldn't that be annoying? It depends on how you look at it. So this is the end of that little line that I had earlier in the presentation. It's the last invention that man need ever make, provided that the machine is docile enough to tell us how to keep it under control. That is an optimistic viewpoint, at least from the perspective of science fiction. And it took me about 3 minutes to come up with all these pictures. I had to think longer and harder about the next slide, which is utopias. For your reference, that's 2001: A Space Odyssey. That's The Matrix. That's The Terminator. Robopocalypse is a book that came out this summer, and it's going to be a movie. And then Stealth was a movie about a fighter jet that actually they have these now. They like flew one this summer, but a fighter jet, and then it gets struck by lightning and turns into an evil intelligence. So it's still sci-fi, but the overriding theme is that when the singularity occurs, bad things are going to happen. The robots are going to kill us all. They're going to enslave us and use us for batteries. They are going to, for whatever reason, they're going to feel threatened by us and want to put us out of existence. And this is very much a common theme. And when you talk to people who are interested in the singularity, this comes up very quickly. It's like, is this a risk? Are we, by developing these technologies, putting ourselves at risk? And of course, the consensus of the science fiction authors is yes, we are endangered. The only, Seth said that he has a couple of examples, so we can talk about that during the panel, but the only example of a utopia, and it's not really even a utopia, is the Spock's Brain episode of Star Trek, if you remember that episode, where they live in perfect harmony and they have a brain that runs everything for them and they don't really have to think for themselves. There is this idea that we will be to these super intelligences as our pets are to us. In other words, they will find us amusing and entertaining. They will let us do what we want to do. They will probably spoil us. That's the hope. Another possibility that I think is probably the most likely, and in some senses a utopia, is that they will find us almost entirely irrelevant. Right? If you can imagine super intelligences that can replicate themselves and can put themselves into a different machine every day, and they can create new machines of their own design that do amazing things that we can't even conceive of. They're not going to be interested in us in any particular way, but we can poach off them. Right? So the idea is that we can use the technology development that they have to better our own lives, and so we can continue to exist because we won't matter to them, and yet we'll have these technologies that we're able to be aware of because we are intelligent, because we'll have access to it, to better our own lives. So that's an optimistic viewpoint too. And I guess I'm at about 40 minutes, so I have time for questions. I've left a lot of stuff out because I wanted this to be introductory. But these are some things you could read. Certainly, I didn't actually put on here Kurzweil's book, which is the Singularity is Near, is what it's called. And he talks about a lot of different technologies in that book. In addition to reverse engineering the brain, he talks about indefinite lifespan, so being able to live indefinitely, which it seems to me kind of secondary to the creation of intelligence, because that will come very quickly after that. And so otherwise we have to create all that technology, which is hard. And, why would we want to do it if the robots are going to do it for us? So in any case, the Singularity is Near is the kind of definitive book these days on the topic. But Werner Vinge wrote that's the kind of the original article on the Singularity. This law of accelerating returns, which is very interesting from a technology perspective, whether or not you believe in that the singularity is imminent or eventually going to happen, because it does seem to be true in a lot of technology areas. And then Singularity Hub is a news source for things that are going on that kind of relate to the singularity. I will say that they have a lot of narrow AI things on there, so I'm not, I'm telling you my opinions, in some cases not necessarily fact, but and it's really cool stuff. I mean, some of it is pretty impressive what they've been able to do with just algorithms. So, with that, questions?
You talked about intelligence, particularly it strikes me that you said that the single-purpose machines that could do things like answer questions on Jeopardy or the like, or navigate a car, were actually not displaying intelligence because they could do a narrow problem. So would you consider, let's say, a colony of bees, each individual bee does not have intelligence that perhaps the colony does, or maybe the colony doesn't have intelligence either? So I wonder if you would talk about what, because the first forms of intelligence.
So Adam's question is, what is intelligence? And it's a good question, and obviously, I mean, I restated it that way because that's really what you're asking. And it's a very hard question. In fact, there was a previous DARPA program that we were trying to get involved in called BICA, Biologically Inspired Cognitive Architectures. And it was a pretty interesting program, but it fell apart because there was this constant fighting among the groups that were proposing for how we defined what success was and how we knew whether something was making progress. And it was interesting because all of the groups seemed to be worried that the other groups were going to engineer the problem. Because if you say, at the end of year one, you have to have solved this problem, and then we'll give you funding for the next year, guess what? Everybody solves the problem. They haven't made any progress necessarily toward intelligence. They've just solved that problem. And so any tangible problem, it becomes very difficult to define a set of problems that you can do. The Turing test is a commonly used idea for determining that whether something is intelligent. And the Turing test works as follows. You have a computer in one room with, as Turing put it, a teletype. You have a person in another room with a teletype, and you type basically you're IMing with them, right? And you have to be able to tell which is the human and which is the computer. And by the way, they actually do this every year. There's I forget the name of the group, but they actually do this in London every year. There's a competition, but the competition is to see who can fool the guy, the judge. They do this, but the question is, does that really solve it? If you can fake the person out, do you still have intelligence? John Searle, a well-known philosopher from the 20th century, he's still alive and still working, I think, but he had a thing called the Chinese room argument, which is if you had a machine that could say anything you wanted it to say in Chinese, was it conscious? Was it intelligent? Was it there? So I'm not answering your question because nobody knows the answer to that question. Nobody knows the answer to what is intelligent. Now, the reason I say that those things are not intelligent is because they can't learn, typically, or their learning is very narrow. And they can't then, the Jeopardy computer can't play chess. And it can't use anything that's learned in Jeopardy to play chess. And the navigating Google car, it can't then walk. Okay? It can't then play Jeopardy or do anything else. And it can't go off and figure out what do humans need, right? It can't do any of those things. It can just drive around. And so it is intentionally and necessarily limited in its scope of what it can do. And humans, again, we're the second best solution to everything. We can kind of do anything we want. Eventually, we can build a machine that does it better than us. And that's the interesting thing, I think, with respect to the Singularity, is can it come up with something that does things better than itself? But again, that's not a definition of intelligence either.
Kurzweil talks about the human genome being cracked, and the convergence of machine technology and genomics, somewhere around 2032, plus or minus 5 years or so. I was wondering if you have anything.
Yeah, I'm trying to remember that particular. Was he claiming that genomics would be used for computation? Is that the idea, or was it that we would be able to?
That we are getting close to the point where we can effect our own evolution and evolve in ways that we want to evolve with genomics. And using computers to do that, it's this convergence at this, singularity that somewhere around 2032.
Well, it seems like, first of all, it seems like that's all happening now, rather than in whenever 2032. I mean, we're already changing the genome in certain ways. People are fighting it, but genomes of crops and such, of animals, they've created critters that are only bacteria, but they have a completely synthetic genome. And so the technology there seems to be going very fast. But in terms of being able to evolve who we are, maybe, it's a little hard to see how that connects to the other technologies. Do you try to engineer genomic evolution, this engineered evolution via the genome, and connect that somehow to the neural implant that you've put in your? I don't really know how they connect. Maybe they converge. This idea that these technologies will converge at the same time seems odd to me. It's like, well, how do we know when exactly we're going to get to a certain point with each of them? And Kurzweil has very specific predictions about what year things are going to happen in. Just mark it on your calendars. 2045 is when Kurzweil says the singularity will happen. And again, remembering that this is a point where things just start to go so fast we have not even any concept of it. So it is kind of a point in time. So he says 2045. So I tend not to think of it in those terms, in the genomics and the other sciences terms, because I think the simulated intelligence or the cyborg idea will be the thing that happens fastest, and is probably the biggest driver of all of it. But I could easily be wrong about that.
So the question I have is, I guess I'd start off by saying the stock market, they're actually looking at it this week because 1/3 of all the stock trades are done via computers, and it's gotten so complicated that no individual or group of individuals can go to the government and say, yes, it's safe and it's not going to destroy these things. Are there examples of that already we're seeing right now, that systems have gotten so complicated that we've created that we don't even understand as individuals?
Well, so we have to back off for a second. So the question is, are there systems that are so complex that involve computers that they're so complex that we don't understand them? And I think let's back off for a second and make clear that we don't understand how we work. We don't understand how our own society works. We don't understand how economics works. I mean, we know some things about it. We don't know how physics works. We can't predict three bodies interacting gravitationally beyond a certain point. We can't predict the weather beyond yesterday. There are so many things that are systems that we don't understand, that we like to think that we understand some things, but we really have a huge gap there. Now, introduce computers into the equation, and really the very simplest piece of software, we have no idea how it really is operating, right? I mean, we understand the principles of the different layers of technology in which it's operating. We try to control the electrons at a low level. We try to control the architecture of the machine. But beyond 10 lines of program, we probably don't really completely understand it and what's happening. And so I think that we very quickly reach that point. Maybe what you're getting at in that context is, are there systems that we kind of have there are no patterns or no understanding that we have really, that it kind of completely goes away, that we have no control over and it's not under our control anymore? That's a pretty interesting question. I think we've created a lot of systems like that. I think, you know, Google has gotten to be like that. You know, clearly the stock market has been like that for a long time, a couple decades even. So you know, I don't think you have to look very far to find examples of it. I think the examples that you have to look harder for are things that we really do understand.
So, actually, why don't we wrap it now, and then we're going to bring up a panel, and then we're going to go back into conversation and discussion, but it will be not just Dave, it will be more people. So give us about 5 minutes to set up, and we'll start at the top of the hour. Thank you, Dave.